Hi, everyone. This is a recording to go over the homework solutions to the homework problems from 8.6 to 8.8. So let's go through the homework solutions one at a time. First is 8.6, number 6. So for that problem, it says find the power series representation for the function and determine the interval of convergence. So the function given to you is f of x equals 1 over x plus 10. So I wrote it in the following form. First I thought I factored out a 1/10. And so you have 1/10 over 1/10 times 1 over 1 plus x over 10. And so that's equal to 1/10 times 1 over 1 minus negative x over 10. And so this is equal to 1/10 times the series representation of 1 over 1 minus negative x over 10, right? So 1 over 1 minus negative x over 10 is a geometric series where the common ratio is negative x over 10, and the first term is 1. And so I wrote it like this. And so now take the absolute value of a sub n plus 1 over a sub n. You get the absolute value of x over 10. Set that to be less than 1. And that happens when the absolute value of x is less than 10, which is x values strictly between negative 10 and 10. Okay, since it's a geometric series, it does not converge at the endpoints. And so you have the interval convergence is the open interval from negative 10 to 10. Okay, so that's number 6 from 8.6. Number 17 is another problem in the section. Find a power series representation for the function and determine the radius of convergence. Okay, so the function given to you is f of x equals x over 1 plus 4x squared. So I let g of x be 1 over 1 plus 4x, or 1 plus 4x to negative 1. Then g prime of x is negative 4 over 1 plus 4x squared. Okay, so I set h of x equal to 1/4 times 1 plus 4x to negative 1. And so that means the derivative of this thing is now 1/4 of this derivative, which is negative 1 over 1 plus 4x squared. So the function we're going to care about is h of x. We started with this g of x, and the idea was to see, since there's a 4 here, I want to get rid of it. So I just thought of 1/4 times this function to get rid of that 1/4 in the final answer there. Okay, so we have h of x is equal to 1/4 times 1 plus 4x, which is equal to 1/4 times 1 minus negative 4x. So I've written it in this form, so I can write it as a power series. And so you get 1/4 times 1 minus 4x plus 16x squared minus 64x cubed plus dot, dot, dot. The common ratio is negative 4x, and the first term is 1. Okay, and so I multiplied by 1/4 here to get this sum, 1/4 minus x plus 4x squared minus 16x cubed. I'm just multiplying each of these coefficients by 1/4, distributing the 1/4. Okay, so that's h of x. So h prime of x is just differentiating a power series, is differentiating term by term and adding the derivatives of each term. So you have derivative 1/4 is 0, derivative of negative x is negative 1, derivative of 4x squared is 8x, derivative of negative 16x cubed is negative 48x squared. And so you get this alternating sum here, and it's equal to negative of 1 over 1 plus 4x squared. Okay, because you see the h prime of x there. So f of x is equal to negative x times negative 1 over 1 plus 4x squared. This is f of x. And if you factor out a negative x here, you'll get a negative 1 over 1 plus 4x squared. But that's what h prime of x is, right? And h prime of x can be written as this sum. So instead of multiplying by this, you can multiply, instead of multiplying by this, you can multiply by this sum. By this sum. That's right here. And then that sum, just replace this with this. And so now you have f of x is equal to this. And the radius of convergence is 1/4. Right? And so that's because the common ratio of this sum is negative 4x. So if you take the absolute value of negative 4x less than 1, you get the absolute value of x less than 1/4. Okay, let's put this negative 4x here, right? we took this power series here, right? And we differentiated this one. So the radius of convergence of H is 1/4. We differentiated it to get this part. And that did not change the radius of convergence. It can change the interval of convergence, just not the radius of convergence. Okay, so another problem in the same section is number 29. So for 29, it says we have this integral here. It says use a power series to approximate the definite integral to 6 decimal places. Okay, so we have this definite integral, and it's equal to this. I wrote it under the form 1/1 minus negative x to the 5th. That way I can think of the integrand as the sum, as an infinite sum, instead of as this fraction. Okay. So when you find a definite integral, you're going to integrate term by term. So you get x minus x to the 6th over 6 plus x to the 11th over 11 minus dot, dot, dot. Evaluated from the lower limit, 0 to the upper limit, 0.2. Okay. So we want to approximate this correctly to 6 decimal places, this infinite sum. So this is what you do. You have the definite integral is approximately equal to. And so now we're going to, so what I'm going to do is I'm going to choose up to the a sub 2 term. Okay, so you have the a naught term, which is 0.2, and so you have a. So I'm going to choose up to the this term here, and so when you plug in 0.2, you get this. When you plug in 0, all the terms become 0. So you're subtracting 0 here. Okay, and then okay, so then this is to within 0.000001, and so then this is equal to this. Okay, and that's because if you were to look at the next term of the sum, right, the x, the 16th over 16th term, then what happens is that that will then be really, really small, and so it'll be so small that it'll be less than the 0.000001. Okay, so okay, so we get it to within that small because the term after it, when you plug in 0.2, is just really, really small, less than that. Okay, so you get that answer. Okay, so for 8.7, number 12, find the Taylor series for f of x centered at the given value of a. Okay, so here's f of x. It's equal to x minus x cubed, a equals -2. So the Taylor series for f of x is equal to this. The sum from I equals 0 to infinity of the ith root of a at a over I factorial times x minus a to the I. Okay, so what we want to do is we're going to, the problem says a equals -2, and we have this. So we just find we'll go term by term. So when I equals 0, the 0th derivative of f at -2 is just f at -2. So that's -2 minus -2 cubed. Plus, when I equals 1, you have the first derivative of f, which is 1 minus 3x squared. So you have 1 minus 3 times -2 squared. That's f prime at -2 times x minus -2, which is x plus 2. And then if you divide, and if you raise to the first power, it's just x plus 2. Dividing by 1 factorial is just dividing by 1, stays the same. this I equals 2 term, you have the second derivative. So the first derivative is 1 minus 3x squared. The second derivative is negative 6x. So it's negative 6 times negative 2 for the second derivative divided by 2 factorial times x plus 2 squared. Now the next term, the third derivative is negative 6. So that's negative 6 over 3 factorial times x plus 2 cubed. But now the fourth derivative is 0. The fifth derivative is 0. The sixth derivative is 0. All the remaining derivatives are 0. So all the terms after this term are 0 in the sum. And so this infinite sum becomes the sum of these 4 terms, and then another sum of infinitely many zeros. Okay, so the entire sum is this. And so you just go term by term and you do the arithmetic, and you get 6 plus negative 11 times x plus 2 plus 6 times x plus 2 squared minus x plus 2 cubed. So that's number 12. Okay. Number 18, it says, find the Taylor series for f of x centered at the given value of a. So you have f of x equals the square root of x, a equals 16. This is the Taylor series for f of x again. And so again, we're going to go term by term. When I equals 0, you get this. When I equals 1, you get this. When I equals 2, you get this. And then you keep adding because the terms don't become 0. And so I did the first 3 terms, and these are the first 3, and then it's plus dot, dot, dot. So that's the Taylor series for f of x centered at a equals 16. Okay, so that's number 18. The next one in this section is number 32. And it says, use the Maclaurin series in table 1 to obtain the Maclaurin series for a given function. Okay, so the Maclaurin series table is on page 490 of the textbook. Okay, so the one I'm going to use here is the ln one. Okay, so the ln one I wrote right here, ln of 1 plus x is equal to the sum from n equals 1 to infinity of negative 1 to n minus 1 x, negative 1 to n minus 1 times x to the n over n. This is the thing you need from that table on page 490. But I suggest you look at the table, you know, as to help you understand this section. So it's on page 490. It's right at the top. Okay, this is the form we're using from that table, 490. Okay, so f of x equal to x squared times ln of 1 plus x cubed, this function. And so we want to obtain a Maclaurin series using this equation. Okay. Well, first I'm going to f of x equals x squared times the sum from n equals 1 to infinity. So I'm going to express ln of 1 plus x cubed using this formula. So to use this formula, I'm just going to replace the x here with x cubed. And so I'm going to get the sum. And instead of an x being raised to the n, I'm raising x cubed to the n, right? I'm just substituting. Raising x cubed to the n is x to the 3n here, right? But we have an x squared here. So if we move the x squared into the sum, we're multiplying all the terms to the sum by x squared. So you have x to the 3n plus 2. The plus 2 is from the x squared, moving it into the sum. Okay? And so now that's the sum. That's the Maclaurin series representation for f of x. Okay, next is 63. So for 63, it says find the sum of the series. So here's the sum. I'm going to write it in the form sum from n equals 1 to infinity of 3 to the n over n factorial. That's because if you look at the numerators, you have 3 of the first, 3 squared, 3 cubed, 3 of the fourth. If you look at denominators, you have 1 factorial, 2 factorial, 3 factorial, 4 factorial, so forth. So the pattern is that these terms are represented by 3 to the n over n factorial, where n starts at 1 and goes to infinity. You add them up. Okay, so what I'm going to do now is I'm just going to change the starting point from 1 to 0. And so when I do that, when I start the sum from 0 to infinity, I'm adding an extra term. The term is when n is 0. So when n is 0, you get 3 to the 0 over 0 factorial. That's 1 over 1. 0 factorial is 1. Anything to a 0 power is 1. So the extra term we're adding is a 1. So to get rid of that extra term, I subtract by 1 here. So I have a larger sum with 1 extra term minus that extra term I added, which is 1. And the reason I did that is because this sum, the sum from n equals 0 to infinity of 3 to the n over n factorial, that's e cubed. That's the power series representation for e cubed. So you can see that because on page 490, the table of Maclaurin series, if you look at the equation for e to the x, right? E to the x is this sum, right? And therefore, if you plug in x equals 3 here, you get e cubed is equal to the sum, or n equals 0 to infinity, of 3 to the n over n factorial. And so we see that this sum is equal to e cubed. And so I've now gotten this sum to be part of the expression by adding the extra term and subtracting by 1. And so that means we have e cubed, which is this sum minus 1. Okay, so that's 63 and 8.7. Okay, and so the last section is 8.8, numbers 12, A and B. Okay, so for number 12, A is, well, first f of x is equal to sine x. A is equal to pi over 6, n equals 4, x is between 0 and pi over 3 inclusive. So it's in the book right there. A is approximate f by a Taylor polynomial with degree n at the number a. Okay, that's t sub 4 of x. So t sub 4 of x is degree 4. And so we're going to do this at a equals pi over 6. Okay, so t sub 4 of x is just the Taylor series, but you're stopping at this term. So you have the 0 term, 1 term, 2 term, 3 term, and 4 term. So you're stopping there. Okay, and so you just plug in the terms of the Taylor series up to here, you know, involving taking the derivatives of sine of x and plugging in a, right? Okay. No, wait. And so, okay, so here, okay, so 0, 1. So this should be divided by, okay, I can modify this. This should be divided by 2 factorial, because you have 0 factorial, 1 factorial, 2 factorial, this is 3 factorial, and then this is 4 factorial. Okay, and so you have those extra factorials there, just 0, 1, 2, 0, 1, 2. And so you have 2 factorial, 3 factorial, and 4 factorial. Okay, and so I just had to hit those in, so I have the full correct Taylor series there. Okay, and dividing by 0 factorial, 1 factorial is dividing by 1 in these first 2 terms. Okay, so then that's t sub 4 of x. For part B, it says use the Taylor's formula to estimate the accuracy of the approximation. Okay, okay, so this is unaffected by that change, because what it's saying is that the absolute value of the difference between the actual value and our approximation is equal to the absolute value of the next term evaluated at z, here having a z here for some z between x and a. Okay, so the z here is for some z between x and a. And so since this was t sub 4 of x, we're going to need the fifth derivative of our function f of x. I mean, that's cosine x. So here, the absolute value of cosine x is always less or equal to 1. And so this thing can be bounded above by 1 on this interval of x values. And so you can say that this whole thing is less or equal to plugging in a 1 here. And so you have 4 plus 1 is 5 factorial. So you have 5 factorial here, you have a 1 here, x minus pi over 6, because a here is pi over 6, and then that's raised to the 5th power. And so you evaluate this thing, and so this is an upper bound for that. Okay, so we're estimating the accuracy of our approximation in A with this polynomial by saying that the absolute value of the difference between the actual and this on this range of x values is at most is less or equal to 1 over 120 times pi over 6 to the 5th power. And that's equal to 0.000328. Okay? And so thus f of x is approximately t sub 4 of x for this range of x values within that amount. Okay? Plus or minus this amount. Okay. And so that is going over this homework assignment. Okay? Hope this helped. Okay, bye.